Hey everybody, welcome to Bill Sky, the Assembly Guy. Another ARM video. What we're going to look at today is how to manipulate arrays in an ARM program. And we're going to do it 64-bit. 32-bit is not much different, but it's going to really be a lot like the x86-64 video, which was the Intel video, Intel AMD. And we're going to look at indirect as well as indexed addressing. So if you'd like to look at that video, watch that video, come back to this one, and this one will make a whole lot more sense. I'll try to be as specific as I can. I'll try to be as describing as I can, but it's always good to expose yourself to different platforms, different architectures, and that can help you understand the architecture you're actually studying. So let's get started. Now, I've got a new project that I set up. It's a 64-bit project. And this is on Linux. You can see that I called it ARM 64-bit arrays. And it's just a 64-bit application. So now I've already coded all this and I've already tested it. So what I'm going to do is I'm going to copy from the version of the code that I've already tested. And this is a double word array. In Intel lingo, this would be a quad word array. So I kind of use a little bit of that terminology in this code too. And what this is this is an array of 7 quad values. You can see the first one's all B's, the second one's all C's. They're hexadecimal because they have 0x in front of them. What's kind of weird is the sixth one here has got a 0 in it. I'm not sure why I did that, but I'm sure I did it for some debugging reason. Oh, I see, because it goes B, C, D, E, F, and then 0, and then 1. So that's what I did. And if I wanted to make this compatible with the other ones, I could just put zeros in all of the nibbles, but it does that automatically for me. And then we've got a constant called a qword array.type. That's of size 8 because each double word, each quad word in this case, is 8 bytes in size. Then the size of, which tells you the exact number of bytes in the entire array. And then the length of, which tells you the number of actual 8-byte values in the array. So that's the first one. And then I've got a second one that has just some different values. And the reason I have the second one is because I'm going to show you how to actually, oh, that's the wrong one. Sorry about that. I'm going to show you how to actually add 2 arrays together in this video. So actually it's kind of a cool little video. So this one I called a qword array 2. It has double words in it, which in ARM is 8 bytes. In x86-64 it would only be 4 bytes, but in ARM it's 8 bytes. And those have different values, 1s, 2s, 3s, 4s, 5s. I probably should have made this all 6s. Except for the very most significant nibble, I made it 0. And I'm going to say 0x0 and then all 7s. Okay, great. Now the reason I use those strange values is so I can calculate whether or not the addition was correct, if things worked out correctly. Also, I've got all my constants for this second array. So data-wise, I'm all set. So the next thing I have to look at is the actual code. So let's take a look at the code. And we'll be referring back to that data quite often. So in the code, the very first thing I'm going to do is a thing called indirect array manipulation. Now, indirect array manipulation means that you put the address of the array in a register and then you add values to the register to move to the next value. So for instance, I'm going to load the X1 register with the address of my array. So that's going to put the address of a qword array into X1. And then I'm going to load the first value into X0. So I'm going to say load register X0. And we give reference X1. And that's going to put our first value. Now because these are 8-byte values, we don't have to do any special conversion or anything like that. It just goes in there just fine. Now, if we want to move on to the second array value, I do this with indirect addressing. I say add x1 plus 8. So that will take us to the next value. So without plus 8, with just the address, we're looking at all these B's. with plus 8, it now is going to put all those C's into that same register. Now, I actually do have a way of doing that where you don't have to specify 8. And actually, it wouldn't be 8, it would be hashtag 8. But instead of doing that, I can just say, because I set up these arrays with these constants, I can say a keyword array dot type. And this will add the size of an 8-byte value to x1. So now x1 will have an address in it that's pointing to the next big number. And then I can say load r x0 and dereference x1. So you can actually see right here that we've got some repetition. If we want to get to the third one, we don't have to do anything other than just copying the code. And that's going to go to the third one, to the fourth one, to the fifth one, and so forth. It's just going to put those into that register. Now I think we should go ahead and test this out, and it's actually a pretty easy debug test. I forgot my square brackets. Remember, square brackets mean dereferencing. All right, there we go. So let's go ahead and debug this. And then I'll open a new tab. And let me make this a little bit wider so we can have a little bit better debugging. Okay, so what we're going to be doing is we're going to be looking at, I believe we're going to be looking at x0. So x0 is at the very top. We're going to get through the welcome message. Now we're going to load dereferenced x1 into x0. You can see that we have all B's except for the very first nibble. The most significant nibble is a 0. It should now be all C's, all D's, all E's, and then all F's. So that is indirect addressing. Now, if you noticed, and it wouldn't be a bad idea to notice this, we could do this again, just so you can see. As we're doing this, if you look at x1, every time we go to the next item, the E at the end, the one E at the end of x1 right here, that now becomes 26. So if you take 1E, add 8 to 1E, you get hexadecimal 26. We should add 8 to 26 again. That takes us to 2E. That's 8 bytes away. So that's how you move using indirect addressing, by simply putting the data into a register, modifying the address of that register, and then accessing the data. That's my absolute favorite way of accessing arrays. It does have one major problem though. If you have something like 30 arrays that you all have to access all of the data in position 1 of all 30 arrays, indirect won't work. You don't have enough registers to hold all of the addresses of all of those arrays. So there is another way of accessing arrays and their contents without using indirect. It's called indexed. And I call that indexed array manipulation. And this is more like what you're used to seeing in C and C++ and Java, where you have an array name, square bracket, and then the index. It's not quite the same, but it's very, very close. And this way you don't have to store the array address into a register. You can just use the array name. And so let's take a look at that. So what I'm going to do is now there's a couple of ways you can do this. I'm going to go through, I think there's probably about 3 or 4 ways you can do this. I'm going to go with the easiest way first. I'm going to load into my x0 register the address of a keyword array. Now this is kind of like indirect, except we're not going to add numbers into the x0 register. We're going to tell the assembler, we're going to tell the CPU, do that temporarily for me. And how do I do that? Well, I'm going to load into x1 dereferenced x0, which contains the address of a keyword array, In this case, I'm going to say 0. Now, you don't have to say add 0, but I'm doing it here just for effect. So what that's going to do is that's going to dereference x0. It's going to add 0 to x0 first, not specifically to the register, but kind of in a temporary area, and then it's going to access that array location and put it in x1. And I can do the same thing. So I'm going to say add 8 to it. I'm going to say add 16. So I'm adding an offset to the x0 register without actually adding it to the actual register. It's just being done during runtime. So let me go ahead and make that. Now, what I'm going to do now, so we don't have to go through all this code, is I'm going to put some comments here. I'm going to make this an entire block comment so we don't have to step through all that code. And let's debug this. Okay, so let's get through the welcome to my world. Now, the line right above what's highlighted right now, that is putting the address of a keyword array. And what we're going to do is we're going to watch x1 this time over here on the right. It's going to contain the values. There's my all B's, there's my all C's. Notice over here, the address of the array never changes. So that right there can help you out. Now, you're still using a register for the address of the array, and we're going to get away from that. But for right now, this is another way to do it. And it's going to be all E's, and we could do F's and all that as well. Okay, so what I like to do is I like to call this using constants or immediates. And the immediates is the 0, the 8, the 16, and the 24. Now, there's another way of doing this is I could say using an index register. So you're still using a couple of registers, but we're gonna see about if we can get rid of that completely. So we're going to use an index register here. And what I'm going to do is I'm going to load into x0 the address of my keyword array. Then I'm going to move into x2 an index position. I want to move 0 into x2. Then I'm going to say load the register x1, x0, comma x2. Now this is exactly the same as up here, except I'm not using literals. I'm not using the numbers 0, 8, 16, 24. I'm using a value inside of a register. And then if I want to move to the next one, I simply say add to x2 the number 8. So I can do this like this, and you can see the repeating code. So that would lend itself to a loop or something like that. So let's actually see how this works. And we kind of have to get through the first one. We didn't comment that out. Okay, so here we go. We're going to move 0 to x2. That is our index 0. Then we're going to move dereferenced x0, comma x2, which adds those together into x1. And you can see all the B's. We're going to add 8. Shows all the C's, all the D's, all the E's, and so forth. So it's yet another way of creating a method of accessing the array. This time you can do it more programmatically. So what you could do is you could have the user enter what index do you want to access. They could say, I want to access index 10. Then you would simply say 10 times 8, put that into a register, the x2 register, and then access that data. So we're getting more and more automated as this demonstration is moving forward. So let's take a look. Can we do something like using the array name like you would in a C or C++ or Java program? So one thing I would kind of like to do is I'd like to simply do something like this. Move into x2. Actually, I think it would be load register. Load register into x2 a keyword array, and then add the index x2. Of course, we would move into x2 the number 0. But when I do that, it doesn't build correctly. So maybe we need to say equals right here. It just doesn't build correctly. You can't use the array name like you could in an x86. What about load register x2 comma a keyword array of x2? Could you do something like that? And these are some of the things that you can actually do in x86-64, but it's not letting me do that. So really, the only way to do index register processing is this way. Now, what is the benefit of indexed over indirect? Well, we have a single register here that's going to be our offset. It's going to be our index. Right here, we're at the first one. Right here, we're at the second one. Right here, we're at the third one, the fourth one, and the fifth one. So what good is that? Well, what if I've got 30 arrays? I don't need to have 30 different registers that have the offset value for all 30 of those arrays. I just have one here. Where with indirect, you might need to do something like that, and it wouldn't be possible. So this way, you can have a single index register that then is able to process every one of the arrays. Now let's do something kind of fun here. We did an indirect up here. Let's now create an indirect loop. So we're going to create a loop that allows you to loop through the entire array. And I always like to document things. X0 will be our accumulator. And you'll see why this is so important. X1 will contain the address of our array. X2 is our temporary register. And X3 is our loop counter. So we need a loop counter to say, have we read all of the values in the array yet? So that's what the loop counter is for. X0 will contain the total. What this loop is going to do is it's going to add up everything in the array. X1 will contain the address of the array. X0 will be our accumulator. X2 is going to be a temporary counter or register. And you're going to see how we're going to use that in just a moment. So the first thing we need to do is we need to load register X1. And why am I picking X1? Because I say it will contain the address of our array. Move into X1, the address of our array, which is going to be a keyword array. So there's our address. X3 will contain the loop counter, so we're going to move into X3 a constant, a keyword array dot length of. Now, where did I come up with this? Well, I created that constant right here, right underneath the array that I created. So that's why I can use that right there. So that's going to be our loop counter. I'm going to say, I'm going to zero out our X0. And we really should be putting some comments here. And this is 64-bit. Put the total items in the array. Put the array count, X3, and this is the address. So we've got X0, X1, and X3 all set up. Now, where's X2 going to come in? Well, now we have to start our loop. So what I'm going to do is I'm going to call this indirect loop. And I'm going to create another label down here called indirect loop exit. And you'll see why I'm creating that label in just a moment. So here's our loop. So I'm going to load into X2, that's our temporary register, the dereferenced X1. And if you remember, X1 will contain the address of our array. So I'm going to load our first value. So I'm going to say load a value into X2. Then I'm going to say move, or I'm going to say add X0, the current contents of X0, the value of X2. Add our value to X0. now I need to say, okay, I'm done with the first one. And I want to say now that I want to subtract 1 from our counter. And our counter is x3. So I'm going to subtract from x3, 1. Reduce our counter by 1. Now I want to ask the question, is x3 equal to 0? Am I done? Have I read all of my array values? So I'm going to say compare x3 with the number 0. If they're equal, I want to branch if equal to indirect loop exit. So you can see why I created that label down there. So I'm going to put a comment here. If x3 is 0, we're done. So branch out of the loop. Your first loop in ARM that I've taught you. Now, if it's not equal to 0, I'm then going to add x1, hashtag 8. Now, I might want to say a keyword array, oh, forgot the Q, dot type, go to the next value in the array, and then branch to indirect loop. So there you go. So that is our first loop. And it looks like we're doing okay. We're adding to x0. Let's see if this works. All right, let's debug it. And let's get done with our... Oh, okay, I've lost my way here. Let's make sure that we know where we are here. Oh, I forgot. I completely forgot that we commented all this out. And actually, let's go ahead and comment out the hello world print, because we really don't need that. So let's comment that out. So I know why my very first statement will be this load register. I hope you're learning some strategies on how to debug. All right, here we go. So there's my load register. So that's going to load into x1, the address of our array. It's now going to move the count, the number of items in that array. It's going to move that to x3. You can see x3 there has a 7. We're now going to x0 out x0. Well, it's already a 0, but let's 0 it out anyway. Now the loop begins. So I'm going to load into x2, x1. You can see it's all B's. I'm going to add that to x0. x0 now has all B's in it. We're going to subtract 1 from x3. We're going to compare x3 with 0. If they're equal, we want to branch to indirect loop exit, but it's not equal to 0. x3, as you can see, is equal to 6. So we're going to add 8 to x1. That's going to take us to our next value, and we're going to branch to the top of loop. Now we're going to load into x2. There's our all C's. We're going to add it to x1. Now you've got this big number. I don't even know what it is, but you got this big number. Subtract 1, compare. It's not equal, so it adds and it branches. And we're going to watch x3 here. x3 is slowly moving down in value. It's down to 2. It's down to 1. Now it's down to 0. And now it left the loop. And you can see we're at the indirect loop exit. Pretty cool, I think. So I'm going to continue and then quit. So that is an indirect loop. Now let's try an indexed loop. So now, and I'm not going to, I guess I could copy and paste this, but let's go ahead and just start from scratch here. So I'm going to use the indexing register method. So I'm going to say an indexed loop. I'm going to use x0 is our accumulator. x1 is the address of our array. Spelling isn't that important. x2 is our index register. It'll contain what position we want to be at. x3 is our loop counter again. And x4 is our temporary register. Now you might look at this and say, well, holy Moses, you're using more registers than you did in indirect. Well, I've got 2 arrays here that I'm going to combine into a third array, and you're going to see how we're still going to only use 5 registers in that loop. In indirect, we would have to add 1 or 2 additional registers. So as you have more and more arrays that you're processing at the same time, the number of registers you're going to be using is going to go down. Okay, so let's load into X1 because that's our address, a keyword array. So that's the address of a keyword. I'm going to move into X2. Our starting position in the array, which is 0, I'm going to move into X3. A keyword array dot length of. So X3 is our counter, and I'm going to 0 out X0. And then I'm going to create my indexed loop label, and I'm going to say indexed loop exit label. Kind of like what we did for the indirect. Okay, so let's do it. So I'm going to load a register X4 because that is our temporary register. The address from X1 plus the address from X2. It looks kind of weird because there's no plus sign there, but that's how ARM works. I can say load a register X4 from X1 with X2 added to it. And X2 has a 0 on the first one. And then I'm going to add to X0, X0 plus X4 because it now contains the array position. I'm going to now subtract from X3 our counter. I'm going to subtract 1. I'm going to put compare X3 with 0. If it's equal to 0, I'm going to jump branch of equal to indexed loop exit. Otherwise, I'm going to add to X2 a quad word array dot length or dot type. We want to do dot type. And then we're going to branch indexed loop. So comments would be really great, but I want to get this video over so you guys can go get a beer or get some wine or something. But it assembled great. So let's test this out. Now let's comment out all this other stuff that we've done so we don't get stuck in it with it again. Debugging it. So I'm going to comment all of this out. And let's build it. Great. Now let's debug it. Okay, so we're on the outside of our indexed loop. It's actually very useful to kind of have the code over here on the side, your source code over here on the side with this kind of a GDB debugger. If I can get my mouse to cooperate, and then we've got our GDB debugger here so we can kind of see. So we're actually on this line of code right here in our source code. So we're going to set up our registers. Then we're going to load a value from the array, which is stored in X1. The address is there with X2's index value of 0. We're going to load that into X4. So there's all of our B's in X4. We're going to add that value in X4 to X0 because we're summing up that array indexed this time. Then we subtract 1 from our counter. Is it equal to 0? Nope. So we add the size of each item in the array to X2. And notice how X1 never changes, unlike the indirect method. It's always staying the same because we're using that indexed offset method. Now it's 0, so it's going to leave the loop. So that's the indexed loop. That's the indexed addition loop. Now I want to do one last thing that's really cool. What I would like to do is I would like to sum up these two arrays into a third array. And what I did was I created a variable right here called sum keyword array dot skip. And what that does is it skips the number of bytes in my keyword array. So what it's going to do is it's going to allocate enough memory to store everything that's in here added to everything in here as separate array values. And I'm actually going to show you how to view that in the debugger, how to actually view the memory in the debugger. It's a pain in the neck, but it's kind of neat to actually see it happen. So you can actually watch the memory. Okay, so let's get our ducks in a row here. And I want to make sure I have the debug code. Okay, so let's go ahead and comment out our indexed loop. So you're going to see how this indexed can actually be very, very beneficial. So here's an indexed sum to arrays loop. And I'm going to call this loop indexed sum loop, indexed sum loop exit. Oh, forget the colon there. And now I have to set up my registers, so I'm going to move into x2, 0. I'm going to move into x3. You know what we didn't do? We didn't say what our registers were going to be here. So x0 is our accumulator. x1 is the address for each array. You'll see what I mean by that in just a moment. x2 is our index register. x3 is our loop counter. And x4 is our temporary register. I'm not sure if we actually use that. So we might, no, we do use it. Okay. So we're going to put 0 into our index register of x2. In x3, we're going to put the number of items, just like we did in our other loops. I'm going to 0 out. Oops, I typed that in wrong. Okay, so we're going to 0 out our x0 register. Now what we're going to do inside the loop, we're going to load into x1 because that's our address, a Q word array. So we're going to put the address of our first array into x1. We're going to load x0, that x1 value, or the value from that array, because that address for that array, our first array, is in x1. We're going to put that value offset by x2. We're going to put that in x0. We're going to load into x1 now our second array address. We're going to load into our temporary array, or our temporary register, x1, x2, just like we did for x0. So what happened was, if we look at these in our array here, BBBB will go into x0, 1, 1, 1, 1, all those ones will go into x4. That's what these 4 lines of code do. So now we've got the first one in x0, we've got the second one, the second array at the first position in x4. Now we're going to add to x0, x0 plus x4. So that adds them together. Now we're going to load the address into x1 of our sum keyword array. That's our third array that I set up here in the BSS section. You can see it right there. So that's our third array. So I put that in there, and I'm going to store x0, which is the sum of those first 2 entries of those 2 arrays, store into there x1, x2. x1 is the address of this. x2 is the offset from the beginning of that, which x2 will be 0 the first time this runs. Okay, I'm going to subtract from x3 1. I'm going to compare x3 with 0, branch if equal to indexed sum loop exit. Otherwise, add to our index x2, comma, a keyword array dot type, or I could type in hashtag 8 and then branch to indexed sum loop. So I think the best way to look at this is to actually debug it. And really, I really need to put some comments in here. I'm going to leave that to you. And you can see how we put comments there. Don't take comments for granted. Please put them in there. But I don't think you want to see me typing for the next 10 minutes. So we're not going to do that. So let's go ahead and build this. Make sure I typed everything in correctly. Can you believe it? I typed it in right. And let's debug it. Okay. So we're zeroing out x2. We are putting the number of items into x3, and x2, remember, is our index register. We're zeroing out x0. We're loading the address of our first array into x1. We put that into x0. You can see all the b's. And again, if we take our code over here and go up to the top, there's our first item, all of those b's. Now we're going to put the address of our second array, which is down here. We're going to put that into x1. We're going to dereference that with x2 and put that into x4. So you can see there's all the ones from that array. Now we're going to add those to x0, which would make that all c's. So it added all those ones to all those b's, and we got all those c's. Now we're going to load the destination array, which is our sum keyword array. We're going to load that into x0. We're going to store the value that's in x0, which is all c's. We're going to store that into the address of indexed, I'm sorry, not sum keyword array, which is this third array down here. We're going to store that in there. Now, how do we know it's in there? Well, on GDB, I can do this. And I can see all 7 of the items in the sum keyword array. X means display memory. I want to display 7 hexadecimal. G stands for 8-byte values starting at some word array, and we can see that all C's was just put into that location. I'm going to check X3, and now I'm going to do it again. We store it. I'm going to type that in again. And now we've got all of our E's there. It's pretty neat. We're watching memory being updated as we're processing. All right, well, let's continue this going. Now I could have put a breakpoint here. Let me see. Let me put a breakpoint so we don't have to be pressing enter so often. So let's put a breakpoint. And let's see. I want to put a breakpoint on the line after we store the value. And that's going to be 4000D8. So I'm going to say put a breakpoint at 0x4000. Let's get this right. D8. And I'm going to say continue. Nope, sorry, I said D. Continue. So now we are there. I'm going to go ahead and now type our display command. And there's all of our ones. I'm going to say continue. There's the one, that's the addition of those next two. Oh, there we go. So we're adding the first items in the 2 different arrays, putting it in the first item of the third, and so forth. Let's do it 2 more times. And now we filled it up. So the line of code we're on, we're subtracting 1 from x3. x3 is now 0. Compare, and we get out of the loop. So that is how we took every item. We took all these B's, added them to all the ones, and stuck them in our sum keyword array. Took all the C's, added them to all the 2's, added them put them in the second position, third positions, and so forth. And you can see that resulting array right there. Phew, man. Array processing, it's not too difficult, but you got to get used to it. Practice, practice, practice. Just like on the logical operators for ARM, you might want to go back, re-watch this, follow along. It's always good to read the instructions before you actually do it. But this is really a valuable skill, and the reason it is because everything in computer science, everything in a program is based on arrays, data collection, comparing, adding, averaging, mean, deviation, everything. And this is a very good skill to understand, and we really hope to see you at the next video.